Okay, hello, Algebra 2 students. This unit, I call it a unit because I'm kind of combining two chapters. We're going to be working with probability and statistics. And we're going to start by discussing permutations and combinations. And these examples are going to be kind of observational, I guess you can say. So hopefully this kind of comes through an understanding of some examples here. So our goal is going to be to count permutations, to count combinations. And we'll start with this. How many different ways can you choose a sandwich, a side, and a dessert from this menu? Now there's a couple different ways you can go about tackling this problem. You could start by making a list of things. You could start with your sandwich. So let's say I'm going to have a hamburger. Well, if I have a hamburger, I'm going to abbreviate this. I have a choice of 3 sides. Okay, I could have a potato, I could have beans, or I could have corn. Those are my 3 options. Okay, and then on top of that, I could have a dessert. So from each of those choices I make, there's a third choice to make, where I could have an apple crisp, I could have banana, I could have flan, or I could have rice pudding. And that's going to be the same choice. So I could go hamburger, beans, and then those 4 choices of dessert. Or rice pudding, and then 1, 2, 3. Same thing here. I could have apple off of the choice of hamburger, corn. I could have apple crisps again, banana, flan, or rice pudding. Now you can use these trees, but we know that I'm going to have, well, how many choices here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'm going to have 12 choices here. So if I choose a hamburger, I have 12 choices. If I choose a cheeseburger, well, that's going to be different because then I have a cheeseburger and then the same choices. I could have a veggie burger and the same choices at the end, or PB&J and the same choices at the end. So really, what we're doing is we're taking 12, because we know once we do one of these trees, well, I do 1 tree for each sandwich. There's 4 sandwiches. That's 4 times 12. We know that there should be about, well, 48 choices. However, there's a different way to think about this. How else could I get 48 from these things? Pause the video and see if you can figure that out. Okay, and I guess I should give you a little structure if you're coming back from pausing the video. Well, we know that there are 4 sandwiches, there are 3 sides, and there are 4 desserts. If you take, well, I have 4 hamburgers paired with 3 different sides paired with 4 different desserts gives me a total of 48 sides. That is basically, we just stumbled upon, the fundamental counting principle, which says if an event M can occur in lowercase m ways and is followed by an event N that it can occur in n ways, then event M followed by event N can occur in m times n ways. So if we want to think of sandwich as event S, you want to think let's do sandwich as W for which. Sandwich as W, side as S, and dessert as D. Well, the way you find that, event S, W, S, D, is the number of ways that sandwich can occur, 4 times the number of ways that sides can occur, 3 times the number of ways desserts can occur, 4 again. So that's what the heck that means. All right, now, for example, this is another common example you would have seen before. How many different outfits can you make with 2 pairs of pants and 3 shirts? So we're just making a single outfit with these things. Well, think of pants as your event. How many different ways can pants occur? They can occur in 2 ways. How many different ways can event shirt occur? 3 ways, 2 times 3 equals, well, there's 6 outfits. And if you made a decision tree like we did above, or I guess just a tree diagram like we did above, you would still come with 6 total outfits, okay? So that's kind of how that works. We can use the fundamental counting principle to find other things as well. So we have this example. If the first license plate, this one on the left here, is to be made with the second option being a letter, that means that in the second spot it has to be a letter, and the rest are being a number, the rest are numbers, we want to know, well, and I guess we have this other license plate where it's entirely composed of letters. They still have 6 spots total. Well, we want to know which design can create more possible plates. And what is the difference between the 2 possible plates? And to think about that, well, let's go to this first one. We have 6 placements. And we have a special placement here. Well, we know that these red spots are going to be digits, and this blue spot is going to be a letter. And we can do replacement here. It does not matter if you have the same digit after another, or it does not matter if you have the same number after another. We're going to pretend. I actually have no idea. Well, how many options do I have in this first spot? And you might just think that there are 9, right? Because you can't have 10, that's a 2-digit number. But you have to include the number 0. So really we have 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. That gives us 10 total options. So there are really 10 options here multiplied by, well, how many ways can the number or a letter occur? And this event can occur in 26 ways. Again, this number can occur in 10 ways, 10 ways, 10 ways, 10 ways. And we're going to multiply all of these things. Okay, now over here, it's going to become clear. If these are all letters, well, we have more letters than we do than single-digit numbers. So very clearly, this should be the larger number. How many letters do we have? Well, we can do 26, we can do 26, we can do 26, so on and so forth. So really, this problem just becomes 10 times itself, well, 1, 2, 3, 4, 5 times 26, and this problem becomes 26 to the 6th power. And you plug these in, and very clearly, the one that's on the left is going to have fewer options, and you multiply that out, and you should get 2,600,000 possible license plate combinations. That's probably more license plates than that will ever exist to people in South Dakota for quite some time. And then the one on the right is going to be, well, you plug that in, you get, what do you get? 308,915,776. So very clearly, the one on the right has more possible license plate combinations. So that's, what's the difference between the two possible plates? I guess we could subtract that and find the number, but I don't really particularly care. This is how you would find these, keeping in mind that we can reuse these letters and we can reuse these numbers. Okay, now, however, what if things needed to be arranged in a particular order? Up here, does the order, I guess, that you put a license plate in, does the order I have this in, does that matter? So really what I'm asking is, well, this license plate is 2D1068. Does the order of those numbers matter? And the answer is yes, the order does matter. If I had, well, the same numbers but in a different order, it'd be a different license plate, wouldn't it? If I had, let's say, 1D2806, that would be a different order. I'm still using the same numbers. Okay, so if the order does matter, this order particularly matters, this license plate I just created, even though it uses the same exact things this license plate does, it's different. This is called a permutation. A permutation is an arrangement of items in a particular order. Basically, that means order matters. Okay, it's an arrangement of items in a particular order. If I have, like, we're going to go back to pants and outfits again. If I have 3 pairs of pants I must wear in consecutive days, how many different wears can I wear? How many different ways can I wear said pants? Well, on the first day, we're going to have a choice. On the second day, we're going to have a choice. And on the third day, we're going to kind of have a choice. So on the first day, how many choices do I have for wearing pants? Well, you have 3 pairs. That means you have 3 choices. On the second day, how many different choices do you have? Okay, and if you've already worn a pair of pants and you don't want to repeat them because people are going to make fun of you because people are mean, you only have 2 pairs of pants. 2 pairs of pants to choose from. And then lastly, on the third day, you will have exhausted your options. You only have 1. So you'll have 3 times 2 times 1. This is an example of a permutation where order matters. And there is no repetition, I should say. I guess all permutations order matters. But this one is an example where there's no repetition. The pair of pants I wear matter, and the order I wear them in kind of matters. So this is going to be 3 times 2 times 1. Well, that's going to be 6. There are 6 different ways you can do that. Okay, another way to represent this 3 times 2 times 1 is by using factorial notation. 3 times 2 times 1 is the same as saying 3, and then there's an exclamation point. But that's not like saying 3! Sorry, headphone users. It's like saying, it's read as 3 factorial. It is using an exclamation point, but we're not excited. We're just saying 3 factorial. So basically, this just means you're doing 3 times 2 times 1. For example, 10 factorial would be 10 times 9 times 8 times 7 times all the way down to times 1. Okay. One more thing you want to keep in mind here. There's kind of a little trick for factorial. 0 factorial you might think is 0, but it is actually 1. So just keep that in mind. So this is read factorial, and we're going to use this notation in a couple different ways. So we're going to move to this example. In how many ways can you arrange 11 books on a shelf, one after another? And we're going to assume that these books are all distinct books. They're all different books, which means, well, when I place one, the next one's going to be different, so on and so forth. And if you want to just think about how many different ways you can place a book if you have I'm going to poorly construct a bookshelf here. Here's a bookshelf. Okay, now in the first spot, I'm going to put a book. Second spot, I'm going to put a book. Third, fourth, fifth, sixth, seventh, eighth, ninth, 10th, and all the way down until I've placed the 11th book. Well, right away, how many different choices do you have for a book? And you should have 11 choices. You have 11 books. Well, you place one book. How many choices do you have to go in this slot? 10. How many do you have in this slot? 9. So on and so forth, right? You're going to have 7 choices after that. 8. Whoops. Not 8. 6. 5. 4. 3. 2. All the way down to 1. Okay, and another way to do this is kind of an application of the counting principle, but we're not repeating things. We can't repeat it. We don't have 2 books. We can't replace the same book. So we are counting down. And, well, I guess the order kind of matters on this one. We're going to do 11 times 10 times 9 times 8 times 7 times 6 times 5. This is just 11 factorial. And I'm going to show you a little something. You can, if you have a scientific calculator, you can type in factorial. You should have a factorial button. If you have a TI-84, you have a factorial button. You can Google on how to find that. Or you can also use your Desmos calculator to calculate these things. And we're also going to use Desmos for something a little bit later on. But I can just, instead of typing 11 times 10 times so on and so forth, you can go to Desmos, type 11 exclamation point, and it gives you what 11 factorial is. It's pretty neat. And it's going to be, well, we plug in 11 factorial, we got 39,916,800 ways. So there are 39,916,800 ways that you can arrange 11 different books on a bookshelf. Go ahead and verify that by hand and then report back to me. So that's a lot of different ways. It's a lot more than you would think. All right. Now, when we're working with permutations, there is a formula we can use to find things. So if we're doing a permutation, keep in mind permutation means that order matters. The order matters. The order I'm arranging things in matters. This bookshelf, maybe it doesn't matter that the books are in a particular order. It might not be a permutation. We're going to pretend that the order that these books are arranged in does matter. Okay, so what we're going to do is come up with this formula for permutations. For permutations. Keep in mind, permutations means the order matters. The order you're arranging things in matters. So, the number of permutations of n items of a set arranged r items at a time is given by, well, n. There's a bunch of different ways it's denoted. We're going to use this notation because this is what you're going to use on Desmos. So if you have a total number of n items and you're arranging them r items at a time, it's n permutated r times. So what you do is you take that number n factorial and you divide it by the difference in those numbers factorial. So n minus r factorial. Okay? This is read as n permutate r elements. N permutate r elements. Okay, now the way you see it in Desmos, and I'm going to show you soon enough, is n p r, and then you put your n value here, your r value here, and that'll actually perform that operation for you. Okay, but for example, if I wanted to find, what's an example I can think of? Let's say there are, I'm going to use, oh no, there's a race. Okay, we'll see an example soon enough. Okay, now, if I'm taking 5 items and I'm permutating them 3 at a time, well, my n value is 5. That's the same as doing 5 factorial over, in parentheses, well, 5 minus 3n minus r factorial, which is just going to be 5 factorial over 2 factorial. And if you just do 5 times 4 times 3 times 2 times 1, this is going to be unnecessary work, so I'll write it in red. This is the same as 5 times 4 times 3 times 2 factorial divided by 2 factorial. These 2 factorials are going to be reduced. We're going to be left with just 5 times 4, which is 20, times 3 is 60. Okay, so that's how you do this by hand. I'm going to show you Desmos when you have a lot larger numbers and you don't really want to do things by hand. There's a way you can use Desmos. So if you go to Desmos and you just type in, we're doing permutations, n, p, capital P, lowercase r, and then you put in parentheses, well, what's our n value? We're taking 5 items and we're permutating them 3 at a time. It gives us a total of 60. So you can use Desmos to do these permutations as well, and that's going to be handy when you have a lot larger values. Okay, now, what the heck is an example of a permutation? Let's go over that. So let's say 10 students are in a race. We're all ignoring the COVID-19 stipulations, and we're going to have a track meet. So 10 students are in a race. First, second, and third places will win medals. There's going to be a gold medal, a silver medal, and a bronze medal. Well, does the order that they finish in matter? If they can't tie, well then, heck yes, order does matter. Which tells us that this is going to be a permutation. So when order matters, we're going to do a permutation. Well, how many students are competing? There's 10 runners. And how many ways are we placing them? Well, we're placing them in first, second, or third. You can use an application of the counting principle and say, well, there's 3 places. There's 10 students that can be finishing in first. After that, how many students should be finishing in second place? Well, that leaves 9. After that, how many students will be finishing in third place? And the answer is 8. So you can do 10 times 9 times 8, which gives you 720. This is the exact same thing as doing, well, we're taking 10 students, we're permutating them 3 at a time. We're taking 10, we're picking 3 of them. The order does matter. Well, that's the same as 10 factorial over n minus r, 10 minus 3 factorial. And this is just going to be 10 factorial over 7 factorial. And like we did above when I said that work was unnecessary, the reason these are the same thing is because this is the same as 10 times 9 times 7 times, whoops, I forgot 8. 10 times 9 times 8 times so on and so forth, right? Times still 7 factorial where I'm counting down over 7 factorial. This reduces, and I'm just left with 10 times 9 times 8, which is 720. Once again, if you go to Desmos, I'm going to do that quick. You can type in 10 permutate 3. 10 permutate 3. And you get 720 again. So that's how you can use Desmos as well to verify your work. All right. Now, I don't have a bike lock to show you because we're not in class in person, but let's say I have a 4 combination bike lock or a bike lock. Here we are. And it uses digits 0 through 9. And there are 4, this is a standard bike lock, there are 4 options. So like 1, 2, 3, 4. Okay, someone's trying to break into this bike lock. How many different possible combinations can there be? And this is where it is, a lot of people like to, I guess we'll talk about this in a little bit. We're saying there's 1, 2, 3, there's 4 different slots, right? Okay. Does the order I put these numbers in matter? Meaning, if my code is 1, 2, 3, 4, can I put any different arrangement of those numbers in and it'll work? Could I put in 3, 1, 2, 4? Could I put in 4, 1, 2, 3, so on and so forth, and unlock it? The answer is no. Only 1, 2, 3, 4 will work. So this is a permutation. Order matters. However, the difference between this permutation and the permutations we've seen before is, well, let's pretend it's not 1, 2, 3, 4. Could I repeat numbers? Could I do 1, 1, 1, 1? You certainly could. So really, if we have the options 0 through 9, we have 10 choices for that first slot. We still have 10 choices for that second slot, 10 choices for the third slot, and 10 choices to the fourth slot. So this just becomes 10 to the fourth, which gives us 10,000 possible combinations. $10,000 possible combinations. So this is still a permutation. It's just a permutation. The order still matters, but it's a permutation with replacement. So that's the difference between this and the previous ones. The previous one we couldn't replace a runner because, well, there's distinct runners. Okay, and this one we can reuse numbers. So we can replace those. This is a permutation with replacement. So if you have a permutation with replacement, it's just going to be the number of items you have to the r, n to the r. We have 10 things, we're taking them 4 times, so it's n to the r, 10 to the fourth. All right, so those were permutations. We've done permutations with replacement. That's going to be this type of example. Permutations without replacement, which is going to be like the books, if we're going to pretend they're distinct books, the students, those kind of things. Now we're only going to do, before I move on, we're going to do something, and I guess we'll explain that. We're doing permutations and combinations. Now we're going to explore what combinations are. We're not going to focus too much on combinations with replacement. That gets a little bit more complicated, and we're not going to focus too much on that today. But we're going to talk about combinations in general. So I want to know, how many different ways can you select from that menu before? Let's say you're just only getting sandwiches. You're only getting sandwiches, and we're not repeating our choice of sandwich. We are only taking 2 sandwiches, and we were not repeating our choice of sandwich. Okay, now right away, you might think, well, how many sandwiches do we have? 1, 2, 3, 4. You're saying, well, if I'm taking 2 sandwiches, that's like having 4 sandwiches in the first spot times 3 sandwiches in the second spot. So shouldn't I have a total of 12 sandwiches? Or 12 choices? 12 ways to choose those sandwiches? Okay, and this is where we have to be careful here. Let's actually list this out. So let's say I'm going hamburger, and again, I can't go hamburger. We're doing no repeating of a sandwich. So let's say I go hamburger, cheeseburger. I go hamburger, veggie burger. And then I go hamburger, PB&J. Okay, so that's 3 options. Well, I could also go cheeseburger, hamburger, cheeseburger, veggie burger, cheeseburger, PB&J. I can go veggie burger, hamburger. I can go veggie burger, cheeseburger. I can go veggie burger, PB&J. And lastly, I can go PB&J and hamburger. I can go PB&J and cheeseburger. I can go PB&J and veggie burger. Okay, now very clearly, this is what we did above. This gives us a total of 12 choices, right? But what's the problem with this? What's the problem with this? And if you look at this, you should recognize, and maybe you recognized this a little bit earlier. Well, if I choose a hamburger and a cheeseburger, is that not the same thing as getting a cheeseburger and a hamburger? If I'm going to eat those sandwiches, does the order matter? Not really. So hamburger cheeseburger is the same thing as cheeseburger hamburger. I need to eliminate my repeated cases. Okay, is not choosing a cheeseburger and a PB&J the same thing as choosing a PB&J and a cheeseburger? Yes, it is. Is choosing a veggie burger and a hamburger not the same thing as doing a hamburger and veggie burger? Yes, it is. We need to eliminate our repeats. A veggie burger and a cheeseburger, that's the same thing as a cheeseburger and a veggie burger. Get rid of that. Okay, veggie burger, peanut butter. That's the first time we did that. Peanut butter and hamburger. PB&J and hamburger. That's the same thing as hamburger and PB&J. Get rid of that. PB&J and veggie burger is the same thing as veggie burger and PB&J. So we got to get rid of that. So there are 12 total choices, but once we account for the repeated choices, there are really only 6 choices. 1, 2, 3, 4, 5, 6. Okay, we have just come across something. We can't choose 12 different ways because choosing a cheeseburger and a hamburger is the same. The difference between this and a permutation, what we've done before, well, permutation order does matter. The order I choose things in matters. Okay, this is what's called a combination. The order does not matter. Order doesn't matter in a combination. So if I have a hamburger and a cheeseburger, that's the same thing as a cheeseburger and a hamburger. Combinations account for repeats, so I should have fewer combinations. It eliminates the repeated things. Order does not matter. Okay, so a combination... Oh, I didn't get that definition. Let's actually get that definition here. And then I'm going to show you how we can calculate combinations in general here. I guess I don't have a super formal definition for us. A combination is just an arrangement of items where the order doesn't matter. Order doesn't matter. So, the number of combinations of n items of a set chosen r items at a time it's similar notation. It's n choose r, and that's how it's read. N choose r. And it's given in a similar way. It's by taking the number of permutations and then dividing by the repeated cases. So we're going to get this formula in the end. It's just you take n factorial, and it's going to look very similar to permutations. N minus r factorial times n factorial. And that gets rid of the repeated cases there. So, for example, if we have 4 items and we want to choose 2 at a time, that's going to be equal to 4 factorial over, well, n minus r factorial, 4 minus 2 factorial, times n factorial, times, that should be r factorial. Hold on a second here. Whoa, that's not what I wanted to do. Got to pull that back up. Okay, so this shouldn't be n factorial. That was a mistake. This should be r factorial. There we go. And that will account for the repeated cases. If we divide it by n factorial, that would mess things up here. All right, so times r, which is 2 here, 2 factorial. This is going to be 4 factorial over 2 factorial times 2 factorial. If you want to write this out longhand, that's 4 times 3 times 2 times 1 divided by, well, 2 times 1 times 2 times 1, which is just going to be 4 times 3 is 12 times 2, 24 divided by 2 times 1 times 2 times 1 is 4, which is 6. Okay, again, you can still use Desmos for combinations. It's the exact same thing, but instead of typing in P, you type in C for combination. So, and choose R, and we are taking, in this example, 4 and taking 2 at a time. We are going to get 6. Okay. Now back to our sandwich problem from earlier. We had how many sandwiches? Whoops. Yeah, okay, no, that is. Okay, these are the same thing. We had 4 sandwiches, and we're taking 2 at a time, and we're not repeating sandwiches. We're not getting a hamburger and a hamburger. That is a perfectly valid type of thing to do. However, that would be with repetition. So we're accounting for combinations without repetition. So again, combination, order doesn't matter. The order I have a sandwich in doesn't matter. Cheeseburgers and hamburger is the same as hamburger, cheeseburger. So order does not matter. And I'm taking 4 items, 2 at a time. So that gives me 6 total options. So that's how we can do another way instead of writing them out. It's not too bad to do it when there's only 4 of them, but when you have a lot, it's going to be a lot more pain in the butt. So a different way to do this is to just say, well, I have 4 choices. I have 4 items. I'm taking 2 at a time. And that's going to be a total of 6 outcomes if I'm not repeating. If I'm not repeating those choices. All right. So let's move on. That's kind of how you would do that. So what is 13 choose 4? The number of combinations of 3 items chosen 4 at a time. Well, 3 choose 4 is going to be the same as, let me full screen this. 13 choose 4 is the same as doing 13 factorial over n minus r, 13 minus 4, parentheses, factorial, times r factorial times 4 factorial. This becomes 13 factorial over 13 minus 4. 13 minus 4 gives me 9 factorial times 4 factorial. You plug that into your calculator, you should get 715. Let's verify that with Desmos. Go to Desmos here. I gotta make sure this is still recording. I can't remember if I exited out or not. Did I exit out? Nope, we're still good. All right, sorry about that. So we want to do, well, 13 things chosen 4 at a time. Just type in N capital C, lowercase r. We're taking 13, we're choosing not 2, we're choosing 4 at a time. We should get 715. That's exactly what we get. All right. So permutations, I want you guys to say it out loud. Permutations, the order does matter. Combinations, order doesn't matter. So this is the joke that all math nerds like myself like to make. We go up here. Well, if I have a locker combination or a bike combination, it's really not a combination, because if it was a combination, well, 1, 2, 3, 4, if it was truly a combination, 4, 2, 3, 1 would also get me access to that bike lock. And we know the way bike locks in most combinations work is not true. So the nerdy thing to say is, well, it's really not a combination, but it's a permutation. And if we were all there in person, I would have made that joke full-hearted and very seriously and watched you all stare back at me in silence, and it would have been amazing. But this is different times, so I'm just telling jokes to myself while I make videos. Okay, so we're going to end with these examples. Permutation or combination. And I encourage you, before I work through them, I want you to pause them at each junction and figure out what type of thing it is, set it up, and see if you can solve it. So for this first example, a chemistry teacher is dividing his class into 8 groups. Each group submits one drawing of the molecular structure of water. This teacher will then select 4 of those drawings to display, and we want to know how many different ways can he select the drawings. And here's what you want to think. Does the order that he selects these students in matter? Does the order matter? So let's say we have group A, B, C, D, E, F. How many are there? A, B, C, D, E, F, G, H, I, all the way to H, I. Counting's hard. All right. We have this many groups. We're saying, does the order matter? Well, if there's 8 groups and 4 of them are being selected, he could select A, B, C, D. That's 4. Okay. Well, I mean, if he's just selecting 4 to like hang on a wall to display, does it matter if it goes A, B, C, D on the wall or D, B, C, A or whatever a combination of those 4? And the answer is no. The order doesn't matter. They're not winning a prize. It's not first place. There's no first. Being chosen first isn't better than second and so on and so forth. It just matters that there's 4 chosen. So we can say, well, does the order matter? Heck no, the order doesn't matter. Order doesn't matter. So that tells us that it's going to be a combination or a permutation. You should be screaming combination. So if we have 8 groups and we are choosing 4 of them to display, plug that into Desmos, or if you want to type it out, that's the same as doing 8 factorial over 8 minus 4 factorial, n minus r factorial, times r factorial, times 4 factorial. So this is going to be 8 factorial over 4 factorial, times 4 factorial. You should get 70 ways. And let me verify that. Let me verify that's right using Desmos. 8 choose 4. We're still doing combinations here. 8 choose 4. We get 70 ways. Yes, we're good there. All right. So the order does not matter. That is why that is a combination. Now, in this next example, example B, A lottery game works by drawing winners from a total of 25 tickets in a raffle. The first ticket wins $100, the second ticket wins $50, and the third ticket wins $10. We want to know in how many different ways can the 3 winners be drawn. So now there's prizes. First prize gets $100, second prize gets $50, third prize gets $10. Does order matter? And the order matters now. Because first place is not the same as second place is not the same as third place. If they are all the same cash prize, then the order wouldn't matter. But the order that they're drawn in does matter. So that implies, well, if the order matters, it's a permutation. It's a permutation. Okay, so if order matters, it's a permutation, which means, well, we have how many things to choose from? We have this raffle ticket. Imagine this machine, or it's like a lottery ball. I guess they're tickets, so we're not quite doing lottery balls. There's tickets, and they're all being blown around in this machine, and someone's grabbing it. They reach in. There's a total choice of 25 tickets, and we are, well, order matters. We're doing a permutation, 25 permutate, and then there's 3 places. Another way to think of this is if there's first place, second place, third place, how many ways can first place happen? 25. How many ways can second place happen? 24. How many ways can third place happen? 23. You plug that in, you should get 13,800 different ways that the 3 winners can be drawn. Verify this using Desmos. If I just did 25 permutate 3, well, now we're doing n permutate r. And we're doing 25 permutate, we're doing 25, oh, I've got to turn my num lock on here. 25 permutate 3, and we get 13,800, okay? Another way to write this is the same as doing 25 factorial, again, NPR is given by n factorial over n minus r factorial. So this is going to be 25 factorial over 25 minus 3 factorial, which is just going to be 25 factorial over 22 factorial. Or 25 times 24 times 23. 13,800 different ways. Okay, so in conclusion, if the order matters, it is a permutation. And then there are 2 options, where there's repetitions allowed or repetitions not allowed. Okay, if repetitions are allowed, then it's just, I guess let's do this. Order matters. In conclusion, here's what we worked through, and I want to pull up these drawing options. Let's do different colors. I've done blue, red. Let's do this one here. Order matters. That's going to be a permutation. And if order matters, and we are going to say repetitions allowed and no repetition. Well, if repetitions allowed, it's just n pick r, If repetition's allowed, it's not that. If no repetition is allowed, then it's n pick r. If repetition occurs, like in that bike lock example we saw earlier, then it's just n to the r. Okay, now if order doesn't matter, then it's going to be a combination. And we didn't do an example with repetition. We're not going to worry about that right now. But if there is no repetition and it's a combination, the order does not matter, then it's going to be n choose r. And again, these formulas, n to the r is easy enough to remember. N permutate r is given by taking n factorial over n minus r factorial. N choose r is given by doing n factorial over n minus r factorial times r factorial. Okay, so that's kind of a quick look into permutations and combinations. They just give us the total number of ways that things can occur, and you have to determine whether things are going to repeat or not repeat, whether order does or does not matter to do these types of things. But they just tell you how many different ways they can occur. These are going to be useful for finding probabilities, which is what we're going to work on, not today, not tomorrow, but next week. So, good luck with everything. Hopefully your tests went well. Have a good day, everybody. And remember, as always, stay safe out there.